Am I audible? Let me know. Hello.
Hello, sir. It's audible.
Okay, so today we will learn how to design a culvert. I will write the question. Design a culvert.
Okay.
Design of culvert. It is also called as slab culvert. Okay, so I will give you the question here, and then we will start the designing of a slab culvert. Culverts are small bridges. The span of the culvert is 6 meter or less than 6 meter. So if the span of the bridge, if it is 6 meter or less than 6 meter, that bridge is called as culvert. So it's a kind of a small bridges. So first we will try to understand, we are dealing with the design of bridges. First we will try to understand how to design the small bridges that is known as culvert. Okay. So in also in national highway, you get small pipe culvert, box culvert, slab culvert. So those are the small bridges that you get in the national highways. Okay. So design a reinforced concrete slab culvert for a national highway. For a national highway crossing to suit the following data. Crossing to suit the following data. Okay. So here they have given the width of the carriageway. In the previous class, I told you what is carriageway. Width of the carriageway. It is two-lane bridge. Two-lane bridge. The width of the carriageway is 7.5 meter wide. That is what is given in the data. Then footpath is given. Footpath 1 meter on either side. 1 meter on either side. Clear span of the bridge is given. Clear span. This is equal to 6 meter. Then they have given the wearing code. In the previous class, we have discussed what is wearing code. Wearing code. Thickness of the wearing code is given to you. Here it is 80 mm. Okay. Width of the bearing. It's a kind of support that is, you provide to the bridges. Sometimes it is also known as bearing. Bearings are the support that is provided to the bridges. Okay. So they have given the width of the support or width of the bearing. Width of the bearing. Width of the bearing is given to you. That is 400 mm. 400 mm. Okay. Then we have the material, what type of concrete we are required to use, and what type of grade of steel that we are required to use. That data is given to you in the problem. Materials, what kind of material you are required to use. Materials, M25 grade concrete, and Fe415 steel. So these are the material that you have to use in the design of bridges. And note that M25, it uh, is the least grade of concrete in the bridges. You cannot provide M20. You have to start with M25. Then you can, increase the grade of concrete. So M25 is the least strength of concrete that is provided in the bridges. You can note it down. Okay. And they have given what kind of loading the culvert is subjected. So in the, we have different kinds of loading, and the loading will be specified in the problem. What kind of loading you have to use for the design of the bridges. Okay. Sometimes they will give you tracked vehicles. At other times they will give you wheeled vehicle. So they will specify what kind of load you are required to apply on the bridges in order to design the bridges. Okay. So here they have given the loading IRC class double A tracked vehicle. So most of the time, in the design of bridges, tracked vehicle will be given to you. And you need to learn how to design the bridges by using this kind of loading IRC class double A tracked vehicle. In one class, we have discussed in detail, what are the dimensions of different IRC loading that we have discussed. Okay. So these are the given data. This is the problem statement that we have. So by this problem statement, we have to design the culvert. Okay. So again, I will write the data, what data they have given. Okay. So clear span is given to you. Clear span. Note that this is simply supported bridge. It is here, it is not specified. So bridge is like this. You have one slab, and then you have the bearing. Then you have the bearing. Okay. And the width of the bearing is 400 mm, means width of the support. And the clear span, this is the clear span, that is 6 meters. So in this type of bridges, you only have the slab, you don't have the girders. In case of slab culvert, you don't have the girders, you only have the slab that is provided over the simply support. Okay. Clear span is given to you, width of bearing is given to you, width of bearing, width of bearing is given, that is equal to 400 mm, right? Which kind of loading they have given? IRC class AA tracked vehicle loading is given to you. IRC class AA tracked vehicle, and you have to use M25 grade concrete and Fe415 steel to design the bridge. Okay. So this is the first step. You need to write the data. What data is, the main data you have to write here. In the second step, you have to decide the, you have to decide the depth of slab. Depth of slab. What should be the depth of slab? And you also have to decide what is the effective span of the bridge. What is the effective span of the bridge? Okay. So we have, approximate method by which we can decide the depth of the slab. The depth of the slab can be decided by some approximate method. Okay. So this is L by D, L by capital D equal to 15 or L by capital D equal to 12. So what is the clear span? L is the clear span. Clear span that is 6000 mm divided by 15 equal to capital D. So here it is coming as 400 mm, and see it can be between 12 and 15. L by D can be between 12 and 15. And from that you need to get the depth, overall depth of the slab. Okay. Here it is 6000 divided by 12 equal to capital D, and you're getting it as 500 mm. So this is one approximate method by which you can find the depth of the slab, depth of the bridge, we can say. And another approximate method we have, in case of slab culvert, the depth can be calculated as 80 mm per meter span of the bridge, per meter span of the bridge, per meter span of the bridge. So this is another method by which we can find the depth of the slab. So per meter span of the bridge, what is the span of the bridge that we have? 80 mm into per meter span of the bridge. So our span is 6 meter. So this is coming as 480 mm. And you see which one is maximum out of these three, which one is maximum? And that depth you need to provide for the slab culvert. So overall depth, overall depth, capital D equal to 500 mm. So this is your overall depth. Okay. Now from the overall depth, we have to find small d. Small d equal to capital. All of you know. See, this is very near to RCC. We are invoking the knowledge of RCC. You have the overall depth. From the overall depth, you're finding the small d. You need to decide the clear cover, right? So capital D minus clear cover minus you know, half of the diameter of the bar. So this is how you will find a small d. So you know the capital D, you have just calculated, and you need to decide what is your clear cover based on the exposure condition. And you also have to assume the diameter of the bar, and you will get half of the diameter of the bar. Okay. So what I will do, I will assume the condition as moderate. The exposure condition is moderate condition. And for the moderate condition, the CC will be equal to 40 mm. Okay, CC will be equal to 40 mm. Right. We will also assume that we will be using 20 mm diameter of the bar. If we are using 20 mm diameter of the bar, half of the diameter of the bar will be 10 mm. Okay. Small d equal to capital D is 500 minus CC is 40 mm minus half of the diameter of the bar is 10. So small d is equal to 450 mm. You got up to this? Class, you got up to this? Any question? So we have decided the overall depth. We have decided the small d in our step. That is depth of slab. Now we will have to decide the effective span of the bridge. What is the effective span of the bridge? Okay, that we will decide. So effective span of the bridge, in the same way we need to find as we find the effective span of the slab in case of building the bridge, effective span of the culvert. How you are deciding the effective span of the slab in case of RCC building? In the same way, you have to decide the effective span of the bridge. So you are invoking you are using IS 456-2000. Okay, effective span, effective span effective span is the least of two things. Okay, is the least of number one, clear span plus effective depth, clear span plus effective depth. So what is your clear span? Clear span is 6 meter plus effective depth in meter. Effective depth in meter is 0.450. So this is coming as 6.45 meter. So next we have center to center distance between the support. For example, this is your bridge. Then here you have the support. The clear span is 6 meter, right? The width of the support is 0.4 meter. Okay. Now you need to decide what is the center to center distance between the support. So center to center distance between the support will be 6.4. Okay. 6 plus 0.4 divided by 2 plus 0.4 divided by 2. So this is coming as 6.4 meter. So list of two means this is the list of the two value, and it will be your effective span of the culvert, effective span of the bridge. Okay, effective span of the bridge. Now we'll see the cross section of the bridge, cross section of the deck. It is also called as deck. The slab, the bridge slab is also called as deck, deck of the bridge. Okay, so we will see, cross section, how the cross section is drawn. The cross section of deck, the cross section of the deck, the deck. This is also known as slab. Okay, is shown in the figure below. Is shown in the figure below. Okay, so so this is how the diagram will be. Cross section of the slab or cross section of the deck. They have given 1 meter width of the footpath. Footpath is 1 meter, right? Then above this you have the wearing coat. This is the wearing coat that you have. So what is the dimension of the wearing coat that they have given? The dimension of the wearing coat is 80 mm. And from here to here, this is known as carriageway. Carriageway. Okay. And the dimension, the width of the carriageway is 7.5 meter. 7.5 meter. And this is the slab, the depth of the slab that you have decided. The overall depth of the slab, capital D equal to 500 mm. So this is how the cross section of the bridge will look. The 1 meter width of the footpath. This is the footpath that we have. Then here we have the carriageway, and in the carriageway we have 80 mm wearing coat, and then we have the depth of the slab. Okay. Next step we need to find the dead load for bending moment. Number 3, dead load bending moment. Dead load bending moment. Okay, dead load bending moment. Dead load of the slab. Here you see in here we have the slab and we have the wearing coat. Okay, so first we need to find dead load of slab. Dead load of slab. The overall depth of the slab is 500 mm into density of the concrete. So density of the concrete can take 25 kilonewton per meter cube, or you can take it as 24 kilonewton per meter cube. Again, it depends on it. Okay. So 0.5 into density of the concrete, I will take 24. Okay. So this is coming as 12 kilonewton per meter square. Then we have considered the slab, dead load of the slab, the concrete area we have considered. Above concrete area, we have the wearing coat. We also have to consider the dead load of the wearing coat. Dead load of wearing coat. Dead load of the wearing coat. The depth of the wearing coat is 80 mm. And in meter, it will be 0.08 into density of the wearing coat. Density of the wearing coat is 22. Okay. This is given in IRC code. What is the density of the concrete? What is the density of the wearing coat? So all those details are given in IRC 6. Okay, so density of the wearing coat is 22. This is coming as 1.76 kilonewton per meter square. So Total dead load. We are concerned with the total dead load. Total dead load, total dead load equal to 14. Okay, you can just modify it. You are getting 13.76. You can take 14. Again, if you want to take 13.76, doesn't matter. If you're taking 14, there is no issue in it. So we have taken, this is the simply supported bridge that we have, and dead load is, it is constant. It is over the entire span. The dead load is over the entire span. This is 14 kilonewton per meter square. If you are considering 1 meter width of the slab, it will be kilonewton per meter. Okay. And the effective span is 6.4. Now, what is the bending moment? Dead load bending moment. The maximum bending moment, if a simply supported beam subjected to UDL over the entire span, the maximum bending moment is WL square by 8. You know that, okay? WL square by 8. W is 14, L is 6.4 divided by 8. 6.4 square divided by 8. And this is coming as 72. You can round up 72 kilonewton meter. Okay, so this is your dead load bending moment. See the heading, dead load bending moment. After finding dead load bending moment, we are required to find live load bending moment. Okay, live load bending moment, and you need to see what loading is given in the data. So in this problem, the loading is given as IRC class AA tracked vehicle is given to you for the design. Okay, dead load bending moment we have done. Next step is live load bending moment. Live load bending moment. Okay, number 4. Live load bending moment. Live load bending moment. Okay. So in the live load bending moment, you see the live load is having some impact on the bridge. Dead load is not having the impact because dead load is dead. But the live load is, it is moving. So when it is moving on the bridge, it will have some impact on the bridge. So you need to consider the impact of the live load when you are considering the live load. Okay. So there will be some impact on the bridge. We are required to consider impact factor given in IRC 6 2017 page number 31. Page number 31. Okay. So in the page number 31, they have given there is an entire chapter known as impact factor. That is page number 31. So what should be the impact factor for different kinds of loading? For different kinds. Here we have IRC class AA tracked vehicle. What is the impact factor for that kind of loading? So we will see the IS code. I will open the IS code for you. Okay, I will share the screen. Let me know my screen is visible or not.
Yes, sir.
Yes, is it visible? Okay. Okay, I will show you IS code. IRC 6, sorry. IRC 6 2017. Okay, IRC 6, where is IRC 6? IS code 2017. So all of you have the printout of this IS code, okay? IRC code. Okay, so this is known as IRC 6 2017, Standard Specification and Code of Practice for Road Bridges. So we are referring section 2, which is loads and load combination. What type of load that you have when you're designing the bridge and how to combine